SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. In the last class, we started the discussion on the parametric elements. So we discussed what are the various issues of starting that. And then this is one little bit of the board work that is still remaining. And let's look at this one. And we are trying to develop the finite element equations based on this parametric mapping. There are two set of shape functions which we use. For example, for geometric mapping, where we use so this is the one which we depicted. So P to P prime, that's what we use the mapping. And so that's for the geometric mapping. And how the zeta here, a simple element, a square element, how it is mapped into the real element. So this is the parent element and this is the real element. And then, so depending upon the kind of functions which you use, so the complexity of the element in the xy axis will be determined. So from a simple case of quadrilateral to curved elements, and even more curves and complicated curves, so we can attain. Apart from that, we have the primary variable, so that's phi hat, which is defined here, is also expressed in terms of shape functions. Only thing we said that the shape functions here and the shape functions here need not be same. So in fact, so depending upon, you may use four shape functions for geometric mapping and 8 for the primary variable, or even the reverse, 8 here and 4 here. So, or even 4 and 4. So all possibilities are there. So depending upon that, so we classified the element. One is if the geometry is less than the primary variable representation, so then we will call it subparametric, and if they are equal, they are subparametric, and if this is more, then it's superparametric. So it depends upon the complexity of the element. If the geometry is very complex and the variable is not that complexly varying function, so then we may use this one, so parametric, or we use this one. So here, this is the most popular, where we use the same setup shape functions for both geometry and primary variable. And then here, the last one is superparametric, where the geometry is more complex, like in curved shells and so on, but the variable may not be that complexly varying. So these are the various things. In fact, it is just not a question of this one, n prime being equal to n or something like that. So they're going to affect how some of the convergency requirements, are satisfied within the element. We might mention, we may not go into deep into that, but I'll mention as we go along. So now having defined this one, so let us see how we develop the finite element equations. So the first and foremost here is that these things which are, everything is, interestingly, everything is defined in terms of xi eta. All the shape functions are in terms of xi eta. And while we have to actually deal with the curved element as such, for example, the derivative has to be done here in the xy variables, while the functions here are prescribed in terms of xi eta. So first thing is the transformation. So here, so for example, let us just take as an example for 4-node element, okay, isoparametric element, okay. For simplicity, so as I said, we use isoparametric for the one reason, simple reason is that the derivatives and all that are same, whether you are considering geometric transformation or primary variable representation. So that's one thing. The other thing also, as I said, it has few important other properties, which we will see as we go on. So here, this here, so if any function here represented xi, and which is equal to xy, so that means that if f is defined here, the same f holds here, occupying the same transformed position. Okay, so if f is varying here, f also here varies according to the xy position. Okay, so now here, so let's look at this one. So let's just look at this one. I'll just put it in the matrix form just now. So anything given as a function of xi and eta, so the derivative with respect to xi and eta can be related to derivatives with respect to x for any function. Any function. Okay, so the same thing can be written in terms of the matrix form as this. So this is the relationship between the derivatives of any function with respect to x and y can be related to function f with respect to xi and eta. In fact, it is the other way which we want. In fact, this is called Jacobian of transformation. Okay. And sometimes simply written as J. So J is a very important part of this transformation. In fact, here we can do the inverse of this one. So where we have so why this is important here. So as we said here, everything is in terms of xi eta. If you take the derivative with xi and eta here, so you can pre-multiply with J inverse to get its function derivatives with respect to xy. So that means that in fact if there is a variation here from a small delta x, so then here it may be varying like this, so they had to be transformed to x and y axis, right? Okay, so another very simple thing which is of interest is that there's a Jacobian here. If you take the determinant of this one, what essentially it determines is that it is a small volume here, for example, is so the Jacobian here gives you the magnification of this one. Okay, so this gives you the magnification. So that means that it's a small delta j delta eta of a small elemental area. So it will be magnified into the determinant of the Jacobian. So this is some of the things which we do. So how do we determine Jacobian to start with? So Jacobian, which is of primary concern for us, so it is dou x by so remember that x is written like this one here. Okay, just so what we have written here, I'll just represent n1 x1 this is what so here, so this is x written in terms of xi eta because n1, n2, n3, n4 are xi in terms of xi eta, right? Just recall n1 for example is 1 minus xi, 1 minus eta. Okay, so this is for the 4-noded thing. So this now can be written as in terms of so this is in a nutshell a concise form of this Jacobian in terms of the coordinates here. So this n1 for example here is a derivative of this one. So you can write here just for the sake of completeness, you can write it in terms of xi. So it is minus 1 minus theta by 4 and theta minus 1 minus xi. Okay, so and so on. So right, so at each of these places, so you appropriately fill it up with this one, and then there is an n2 which is 1 plus xi 1 minus theta by 4. So you can do that also. So and these are the coordinates of the 4-noded triangle. I mean 4-noded quadrilateral. So in fact, right now what we are talking about is a quadrilateral like this, but it can be curve shapes also. Okay. So what is that which we got now? The Jacobian. Jacobian we can find out in terms of xi eta. So that means that Jacobian is a function of xi eta. So its value keeps changing from here to here to here and so on. So it's a function of xi eta, right? And obviously it's also a function of x12 by 4. Okay. So now that having known this one, so let's assume, so at any point, so you can evaluate this 3 by 2 by 2, and you can also take J inverse. So all these things are becoming more and more complex, are functions of xi eta. So all these evaluations should be done in a computer code, MATLAB or so, and including some of these inverses and so on. So let J prime 1 1, J prime 1 2, so what does this mean is that, so for example, what we need in the next step, if you want to develop the stiffness matrix, K of the element. So we know that K of the element is given as B transpose dB and this is for the element. Okay, so if you know what B, then you just have to plug it into this one here. B is what? The strain displacement relationship. Let's evaluate that. Okay, so where B is what? So it is strain which are given by dou u by dou x B is strain. I will just write it here. So the epsilon, which is, I wrote it as here, as a vector here. So it consists of 3 components. So these displacements, the nodal displacements of the element here will be, what is the size? So size is, it has got 8 components. Okay. So let's slowly go to that. Then let's just see. So let's expand this one. So this is like this. And what we require here, dou u by dou x. So what is that expression? Dou u by dou x expression for here, we have J prime. And what is that? Here, this is the one. So if you want to get a derivative with dou u by dou x, so dou u by dou x, and what is that which we require here? So J inverse, which is nothing but J prime 1 1 dou u by dou xi, and j prime 1, 2 dou u by dou eta. I hope you could see it. This J inverse is nothing but which we call it as J dash, J prime. So it has values J prime 1, 1. So if you want, I can just replace it as so what it means is that if you want to get the derivative with respect to x, so get the derivative with xi and eta and pre-multiply with j11, j12. So similarly, the derivative with y is nothing but j prime to 1 dou v by dou xi dou v by eta. And now we have two terms here. So it is j prime to 1 dou u by dou xi, j prime to 2 dou u by dou eta, and we have two more terms of derivative v with respect to x, so that's j prime 1, 1 dou v by dou xi, and j prime 1, 2 dou v by dou eta. Okay, so this is the expressions. Okay, so this also we can write it slightly longhand. J prime 1, 1. So these things are slightly involved. So the same things I'm writing it here. Okay, so what we have, the derivatives of u and v with respect to xi and eta, right? So that's what we have to write here. This one and then here we have to write this one here. So this and this one we have to write here. And what is this one? Dou u with dou xi and dou u with dou eta and so on. And this we want to write u1 v1 okay, what is u1? I mean, what is here? U with xi, that's what we want here. So that means that you want it with respect to n1 with xi and 2 with xi. So there is another notation here. If I put a comma here, that's equivalent to a derivative. So this is, so here if you want you can write it. So I wrote it. So you should have u with eta. So I wrote it here n1 comma xi, which essentially means that derivative of n1 with xi. So similarly here, this I want u with eta. So the same thing, n1 eta, n2 eta, n3 eta, and 4 eta 0, right? So that's for this one. And the fourth one, v with xi. So the same thing here, but this is N1 with. I hope you can see it. And then B with the eta. Okay, so now what is that which we got? So what is that? I mean, seems to be we have got lost here. So we want it, the strains, okay? Strains are written in this manner. So now, and slowly, this is the derivatives with xi and eta. And finally, this also are converted to the derivative of the shape functions with xi eta, and then the nodal displacements. So this is the whole B. So that's nothing but B. So you can recognize that this here and this. So B is nothing but, so you can recognize for the sake of completeness, I'll write it. So I'm just writing it again. So here, so this is the B matrix. So I'll just write it for the sake of completeness. We use the concise notation for derivatives. In the sense that N1 comma xi is nothing but, okay, and N1 comma eta okay. So this is how we derived the B matrix here. Okay, so this is the whole B matrix, and finally substitute into so the integral here is on B transpose D. D is the stress strain relationship, and here dx dy is there, and dx dy is, as I said, it is Jacobian multiplied by d xi d eta, and then if you want t. So what is t? T is the thickness. And here now the variables are xi and eta. So xi goes from -1 to +1, and eta goes from -1 to +1. So this is complex terms. So they're all pretty involved in xi and eta. So it's not possible to get any complete solution. So all these things have to be done using numerical procedure. Okay, so this is how we calculate the matrices here. Okay, and of course, I think I'll leave that the other part, that if you have the distributed load over the element, how to get the equivalent nodal forces. Okay, we talked about the important steps in the development of finite element equations for isoparametric elements. Having discussed that, there are a few issues that need to be mentioned here. They are about the correctness of this mapping. One is this geometric congruity, in the sense that so since we are having the element in xi eta, and then if you map it here, we are using two neighboring elements. So by mapping, right? So let's just consider 8-noded element like this, and then we use the 8-node. 8-node, we know that it will map complex surfaces like second-degree curves. So if you think that we are for element E here, if we are using the coordinates of this 1, 2, 3, 4, 5, 6, 7, 8, and then this is the mapping of geometry from here, and then this is mapping, as well as if you show the E plus 1, where you use the locations of these 8 nodes which are here, including these 4. So that means that these 3, 4, 5 are common. But since we are using different coordinates as well as different shape functions for mapping this one, is it possible that in one case like this, is it possible that so in one case I wrote it with yellow, in the other case probably I'll mark it with red to be more So in one case the edge is formed passing through 3, 4, 5, but like this. By the other element, is it possible that it goes through 3, 4, 5 like the other way? So this is not acceptable, because the surface, the real surface which is in the xy coordinate, is either some gaps are being formed or some overlapping is taking place, right? Some overlapping may be taking place, which is not acceptable. Is it possible that some gaps or overlapping take place? So this is one question which we have to answer. This is called geometric congruity, in the sense that whatever element you generate here, whatever element you generate here, are they just touching each other, just touching each other? So this will not take place, because if you look at examine this side 3, 4, 5 in the real space. So X will be having N3, X3, N4, X4, N5. So in this, I should mention that let us say this is xi and this is also like this. So that means that the xi is constant here, and eta goes from -1 to +1, right? Eta goes from -1 to +1 as it goes 3, 4, 5, right? So this is -1 to +1. And why did I remove the other N1, N2 and all other 5 nodes? So this is because other shape functions are coordinates. Shape functions are nodes does not come into the picture. Does not come into consideration or picture because they are 0. Because they are 0 on eta is equal to, on xi is equal to +1. So like this N1, N2 and N6, N7 and 8 are 0 on xi is equal to +1. Okay. And of course here also xi is constant here and eta goes from. So the same thing is true with y. Okay. So in fact we can even simplify if we want. So what we will get here, so if you get it, then it will be just 1 minus xi is eta minus 1 x3 to 1 minus eta square x4 this is what it looks like. And so similarly the same thing. So if you work out for, this is for element 1, I mean for element E, so the same thing is can be worked out for element E plus 1, and where 3, 4, 5 is there. So we can go through the same argument here, and then similarly for element 1, similarly we get the same kind of expression. One minus theta. So we can see that so if you work out in detail, so this is what you're going to get. So if you examine these two, so for element E is like this, and for element E plus 1 also, you have identical expressions, which means that for whatever eta you get, say a particular eta you put here, then you find xy. A similar eta you put it here, you get the same xy. So these are identical expressions, same equations, which means that they map identical curves or edges. Okay, so this is very important for us. So that means that whatever you map here for this element E and for element E plus 1, also you have identical expressions. So you will get the same identical edges. So that means that xy is a parametric equation, of course, but whatever the eta you put here, and you will get the same xy values. So okay, so that way, same equation, they map identical edges. So that means that the elements are congruous. So that means that elements which are next to each other will touch each other because the common edges are identical. So if you want, then you can even put it here. So the modified thing which so they have identical edge. Okay, so this is what we are. Another thing is, of course, is that C naught continuity. So the question second issue is that C naught continuity is there or not. What is C naught continuity? C naught continuity is that when you go from one element to another element, using this geometric mapping and using expression for, say, phi xy or zeta. So we are using we are just talking about one variable, phi temperature, and let's assume that it's even 8-noded thing. So what we have here is that so qualitatively explain it here. That means that when you have a point here, let me just point P, okay, PE and P prime, let's say P prime, P and P prime. If P is point on E and P prime is point on E plus 1, just neighboring on either side of this edge, so are they going to have the same phi? So what we are saying is that is phi P in element E, is this phi P prime of element. So the question is that this is important. So on P here, so we have calculated from element E, and on P prime we have calculated from E plus 1. So are they same or not? So we require that for C naught continuity, these have to be same. So this is a fundamental requirement of our C naught continuous elements. So is it so? So for C naught continuity, so we can see here, we have similar expressions. So phi here, phi element E, so we can write a similar expression here, and for that matter, almost on the same edge, right? On edge 3, 4, 5. So we have it as phi 4 and 4, phi 5 and 5 and phi 6 and 6. So this is element E, and E plus 1 also we have phi 4 and 4. So what we can see here is that the element E or E plus 1. So obviously you can see that if you have two neighboring points here, they have obviously mapped from this xy, and so they correspond to the same xi, same eta, right? These two correspond to the same eta, and of course xi being plus 1. So if you put at, say, at xi is equal to plus 1 and eta some value, so they give identical values. Okay, they give identical values. So thus the C0 continuity is maintained. So that means that whatever you get it from here, phi p from element E and phi p prime at element E plus 1. So you will get identical same values, and then that means C0 continuity is maintained. So quickly, there is another small issue which probably, so the question is that the third question here is that will it be the element be able to model or simulate constant state of phi and constant derivative of phi. First derivative. So what does this mean? So so what it means that if phi I are given some values like this, a plus bx plus cy, then what is phi xy? Is it also going to have the same thing? So if you look at phi xy, so which we write as ni phi I, and if phi I, if we substitute this here, so we are assuming that we are giving these values for phi at all the nodes, then what is that which we are going to get here is that a times ni plus b times ni xi plus c times ni phi I. So we know that this ni xi is x and ni yi is y, and so this will be equal to 1. We know that the sum of the shape functions are equal to 1. So this is always satisfied, and it's indeed so. If that is the case, so if sigma ni xi is 1, and we use, what is that which we are using here? So we are using, so ni xi, so if ni is equal to ni prime, so we know that ni xi is equal to x. This is coming from geometry, right? And this is coming from geometry, and so it is x and y. So you can see that we initially gave the displacements in this manner, or y in this manner, and then at any xy we also got the same a plus bx plus cy. So it means that the isoparametric element, so we have used the same shape functions from Ni. So we used Ni prime. So it led to X. So for isoparametric element, so constant state of phi and first derivative are guaranteed. So this is also very important. So for isoparametric element, so the constant state of phi and its first derivative are guaranteed. So this is very much important for solid mechanics also. That means that the rigid body displacements as well as constant strain so can be modeled using isoparametric elements. So that is why the isoparametric elements are very, very powerful, and they can be used to any complex geometry like this one. Okay. Yeah. So these are the three issues which are very, very important for mapping. And then we showed that they are all satisfied, and we can use isoparametric elements for any complex geometry. Okay. I think we'll stop here, and hopefully we'll continue with other topic next. Okay. Bye.